another Central Texas section joint live member group and consultants network meeting, and also co-hosted by a bunch of other live member groups, all in the Region 5 area, in from Denver to Houston, Galveston. So welcome everybody. So I'm gonna give a couple of quick slides here if I can. Now it won't even change for me. Here we go.
Yeah.
Consultants Network is a group of people that we help with the development of members' careers through professional and social networking, yeah, including publicizing the members' skills and sharing potential professional opportunities. And of course, we support the IEEE Central Texas section. And you can see the link down here, r5.ieee.org/CTX-CN for Consultants Network. And for our live member affinity group, to be going back to here, to be a member doesn't cost anything extra other than your standard IEEE membership fee. We have a very easy membership, I guess, to join to become a consultants network member. You just have to join or attend 2 meetings, and you automatically become a member. And that's why we are collecting, names and your email addresses. That's how we track. Now, for the live member affinity group, it's an automatic membership. The formula is being age 65 plus the number of years of IEEE membership is greater than or equal to 100. So some of us are in this category, and when you all reach that, you automatically become a member. Again, you don't have to do anything special, no special membership fees or anything. As a matter of fact, your IEEE dues becomes zero at this time. So it's a nice achievement. So we host monthly meetings with topics of interest to our older members. They are mostly technical, but also we cover other areas such as finance, health, etc. The link is also very similar, r5.ieee.org/CTX-LM for live member. Um, we do need your help. We like to have your help for future meetings. You can suggest topics. These are some possible topics to consider: technology, 5G, 6G, IoT, AI, and smart city. In terms of live member interests, we can also cover finance, hobby, travel, and education. If you've been a lifetime engineer or engineering manager, whatever, we can share your story. We we like to also cover health and aging, engineering and science history. We tend to have 1 to 2 tours a year, um, usually in the Austin area, but I think we have done out of town too. Also, you can consider to be a speaker yourself. If you have a topic that you would like to discuss, please send it to Kai. He's our program manager, and we will get you on the roster. And these are the two groups. These are the people that are helping with us. Now, I apologize. I think the live members officers are probably not up to date. I tried to grab it from the website, but somehow it's not up to date. So maybe we will correct it later. And for the
Okay.
Consultants
It's up to
Network,
date.
pardon?
Oh, okay. Slight change. Yeah.
Yeah, I know there are changes. That's why I look at it, and so I try to get it updated. I go to the website and it's even more out of date than this list. So anyway, I send an email to John and Dennis too, so they can help update that. And the next one, okay, here are some future events this month we are fortunate to have two topics. So today we have one, and in 2 days, this coming Thursday, we have a topic by Sarah LaSalva on 6G wireless technology 2025 update. So you are welcome to join. It's also a virtual meeting like this one.
Yes.
Then in May, we have our Science Thursday at the Bullock, Texas State History Museum. I don't know if John is here to talk more about it, but this is an interesting and very useful to our young prospective future science and engineers because we set up different tables to do experiments to show uh, kids usually from to grade to middle school, not high school, because I guess high school they are already fairly advanced these days. So then in June, we have our second live member conference. This last year we have it here in Austin. This year it will be in Boston, Massachusetts, and this is the website that you can get more information and if you like to participate. So some housekeeping, just mute your audio and turn off the video so that we can maintain the bandwidth. Please use an identifier username so we can also check our roster and update our list of members. You can use the chat box to ask questions, and or maybe you can even ask it live. But probably is during the presentation, it might be better to use the chat box, and then at the end of the presentation, you can turn on the audio and video to ask questions. And now I will turn it over to Kai to introduce our speaker for tonight.
Have you prepared? Okay. Yeah, the topic is where is AI headed, and also brief summary of the research in LLM by Dr. Eric Prince. He's a assistant professor at UT Austin Computer Department, and he's a graduate MIT in 2013. And he worked in a multiple he worked postdoc at the UC Berkeley, and he has been a visiting scientist in the summer for many big AI companies as a consultant. And Eric, please share your screen and start the talk.
All right, thank you.
Okay.
Yeah, so I'm
Yeah. So while Eric is preparing, the speaker in April will be a marketing professor from UT. The topic is a marketing related. It will be a surprise to you. It will be entertainment. It's not a technical topic, but a marketing topic. Okay. So go ahead, Eric.
great. All right. Ah, sorry. This is Zoom is being funny. All right.
Okay.
Is this good? Can you see my screen?
Yeah.
Okay.
Yes.
So Zoom meetings are always a little bit hard to judge how the audience is taking it, and I don't really know you guys and what your backgrounds are and how to pitch the talk. So please interrupt me as much as you want, and if you have questions, please ask questions. Um, that's very important of having a Zoom meeting.
Eric, there's a banner at the top of the screen that's blocking your slide. You need to move that
Okay.
to another screen. There's a rectangular block at the top of the
Yeah, I
screen.
see that, and that's like I think my controls where I'm seeing it, and I'm not sure how to make it go away.
That may be the Zoom.
Yeah, it's the Zoom thing, but I'm not sure how
Yeah,
to
yeah.
make it
The
go
meeting
away.
is being transcribed. So I think you can just read it off. Maybe move your screen down a little bit. Yeah.
Let me
Usually you
try.
can grab it and move it to the side.
Is that better?
Oh, it's worse.
I see what
Where's
a little black. Yeah,
Well,
it's
it's the
okay.
same
Yeah.
as it was.
same as it
Yes.
was? Maybe I can move it around.
Yes.
All right, let me move it around. Let me move it.
那个不是 I 是工工作的工。
There you go.
It's
That's
good.
it.
Very good. All
Yeah.
right. I'm a computer science professor at UT Austin. My background is in theoretical computer science, so proving theorems about computers. But over the recent few years, I've been moving more and more towards machine learning. So just this year, I'm actually on leave from UT, visiting Microsoft Research, where I've been working on large language models, because I think they are shockingly good and going to be able to do a lot of tasks that you used to need humans for, including tasks that you don't think about as being automated, at least not a few years ago. So in particular, proving theorems, which was my day job, I just feel like in the next 10 years will be done completely differently. That they will be able to automate most of what my job was. And so then I don't really want to work on that anymore. It's sort of, I don't prove theorems because it's like chess, where the computer is obviously better than the humans. I want to be doing something that's not automatable. So again, I don't really know what the audience is and how to judge it. So again, there's two parts to this talk. The first part will be just a broad overview of AI as I see it from observing the different AI companies and what the progress has been. And then if we have time, I might go into a more technical bit about 5.4, which is a model that we've been developing at Microsoft Research and that we released a couple months ago, open source, open weight at least. Right. So again, please do interrupt if you have questions. So I think just as a background of why things are changing is Moore's law, which is not dead. And if you look at over the years how much computation you can do per dollar, it has continued to grow exponentially. And so the techniques that people are doing today, they're variations of basically techniques that were developed in the 80s. And they didn't work in the 80s because you had a million times less compute. And what has changed is the hardware is better. And then once you get the better hardware, then yes, the algorithms adapt to the new hardware. But none of this would be possible without Moore's law. The other aspect here is you can look at people like Kurzweil and what they were predicting 20 years ago, 30 years ago, and they were saying, well, how much compute can a brain possibly use? It's not that much compute. If Moore's law continues, we will eventually be able to be doing much more computation on a computer than you are in the brain. Therefore, you should be able to get AGI 30 years ago, he was predicting in the mid-2020s. And if you look at what, and I think he's not far off in terms of having AIs that are able to do most intellectual tasks that most humans can do. So just as anecdotes about my experience with it. So in my classes, so I teach undergraduate algorithms, and if you look at OpenAI's models, GPT 3.5 and came out in 2022, could solve the standard problems, the ones that were in textbooks, the ones that were minor variations of things that are in textbooks. But whenever I asked like an actually interesting problem, it would get tripped up. Or if I did a variation of an existing problem, it would round it to the problem that it had seen before. GPT-4 came out in 2023. Was significantly better. And if I gave it my classes, my exam, it would get an A if I graded it. That said, it made mistakes, and the harder problems, it would get tripped up. O1, this is the model that came out in September, solved all the hardest problems in my undergrad algebra stuff. Still stumped by one in my graduate class. We'll see when the models can solve that, but I'm sure it won't take very long before they can do that. So they're at the point where they can solve class problems very, very reliably. In terms of doing research, right? So if I'm trying to prove a theorem about computer science and computer science or machine learning, it's kind of like a super search engine, like a search engine on steroids, that it has totally superhuman knowledge, and it's not great at using it. So when I'll ask a question, trying to prove, all right, I have some stochastic differential equation, and I'm trying to prove that this SDE converges if you discretize it, blah, 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 right? I have something that I would write a paper on. And I ask it, and it will correctly identify the interesting theorem and knows more relevant theorems than I do, but then it's not able to actually do that calculation very well. So when it actually tries to apply them, it makes mistakes, and you do need a human to go and fix the mistakes. But it is already an enormously valuable tool, and one that can increase productivity substantially in doing CS theory research. And this is not just my experience, this is also what my colleagues have found, that it really knows what's wrong. This is what Anthropic's, one of the leading AI companies, is predicting for the future. This is, of course, selling their own book, so maybe you should take it with a heavy grain of salt. But they're saying that at the moment, they can assist by helping individuals do their current work better, but they're currently rolling out things that collaborate, that will do not just tasks that would take a human a few minutes, but tasks that would take a human hours, on par with experts, so that it basically, instead of being so basically an entry-level software engineer would now be effectively a software engineer manager, where they would manage the AIs and ask the AI to build this thing that would take hours for the human to do, but the AI can do it in a minute. And that, I think, is pretty near-term prediction, is solidly true. They're predicting that in 2 years, they will be able to have a country of geniuses in a data center, that they will be able to find, to do really breakthrough stuff. I think that is less clear, and there's significant challenges to doing that. But I also think it is a real possibility, that these AIs have been working their way up the chain, and it's not obvious that they're going to stop at entry-level work, and they won't continue all the way up to really breakthrough work. In general, all these AIs are, in the past 10 years, are deep neural networks, which means that they are a series of layers where each layer is very, very wide, and then you use a matrix multiplication to go from one layer to the next. So it's order 100 layers of do a matrix multiplication, apply some nonlinearity, and repeat. And most of these language models, all the ones you've probably heard of, are autoregressive language models, which means they try to predict the next token. So given the text so far, the capital O, what is the likely the next token? They'll have some distribution over possibilities. France is likely. Then what's next, is likely. After that, what's likely? Well, Paris is likely. And so the model in order to do this prediction, you need to know a lot of stuff. You need to know what all the capitals of all the countries are in order to accurately predict what is likely to come next in the corpus. Now, one useful mental model for this, I think, is Kahneman's thinking fast and slow. That you have your system one processing, which is like gut instincts, things that you can do in you see it and you immediately respond. That you've got things like image recognition. If I see an image, I can immediately identify what it is. If a chess master looks at a chessboard, they immediately know what are the two most interesting moves to consider. While system 2, slow processing, is where you think really carefully about what to do. So you try to solve a logic puzzle, maybe you have some gut instinct, but then you need to like actually work through a long list of possibilities to really solve it. Or you want to do, if you want to solve it, like once the chess master has their gut instinct, then they need to calculate several moves down, maybe 10 moves down the line in order to know what actually works. And that's system 2 slow processing. And what's interesting is, so in theory, a neural network, like these deep neural networks, they're not that deep. They're like 100-ish layers, which is not that much sequential computation. And it is quite limited. You can easily construct problems that it can't solve with that. But anything that the human brain can do in less than a second, you just look at like how much time does it take a neuron to fire, and it's like 10 milliseconds on that order of that. And so, more than 10 milliseconds. And so the things that the human brain can do in less than a second don't require tons of sequential computation. And they should be doable in these deep, but not that deep. Just, a priori, people would predict this 15, 20 years ago. And then if you look at what computers can actually do, in the old regime, before neural network, they were really good at slow tasks, but not very good at fast ones. So if you wanted to solve a logic puzzle, you could write a computer program that could do that better than a human. If you wanted to solve chess, you had things like Deep Blue that could go incredibly deep. You go a million times, you go twice as deep, so a million times more compute than any human can do, and you can solve chess better than the best human. But they weren't very good at these system 1 processes that humans can do. They weren't very good at image recognition or like having intuition for what to do. And the new regime that neural networks have is that they're actually pretty good at fast tasks. They're actually basically superhuman at basically any fast task. You give them enough data and they can learn anything that humans can do on instinct. But by contrast to the old regime, they're not so good at slow tasks. So if you want to multiply numbers, right? If I want to multiply 10-digit numbers, that's something that computers used to be really, really good at doing. And they're not so good at it anymore. If you ask an LLM to do it, if you ask one of these AI models to multiply 10-digit numbers, it can usually get it right, but not 100% of the time. If you ask it to multiply 100-digit numbers, it probably will always get it wrong. And so it's a different feeling of what the models are able to do. And so there's been progress on this. There's these O1 style reasoning models, and they go from being terrible to being mediocre at slow thinking. They're still not very good, but it is progress. And as an example of something that's interesting is AlphaGo, if you're familiar with that. So that was Google's algorithm for solving Go. And that basically combined neural networks for the gut instinct of like, is this position good? In this position, what moves should be played? With more traditional computer science, computer search, that uses these neural networks as subroutines, much like humans do when they're doing this level. The other, I think, big thing that we've learned over the past 10 years is the bitter lesson, which is as Moore's law continues and as computation gets cheap, the most important thing is to make use of computation in machine learning. So at a small scale, if you don't have much data, you can improve efficiency by hard coding in some inductive bias, by thinking about the problem and coming up with ideas for how to do better. But once you have enough data, you don't want to be hard coding in this bias because the computer can learn the inductive bias better than anything that you can do once it has enough data. So we see a bunch of examples, like if you want to do translation, machine translation, they're not using linguists. They're not understanding parts of speech the way that humans have come up with rules for parts of speech and things like that. They're just given a ton of data of pairwise translations and figure that out. Right? Which makes sense. If you look at language is full, like you learn rules in school, but the rules aren't the actual language. They're an approximation to the language, and native speakers don't follow the rules all the time. And if you want your computer to be fluent, then it also shouldn't be following the rules all the time, and it needs to learn the rules from data. Similarly, in chess and Go, right? If you look at how Deep Blue worked, it had a bunch of carefully hand-designed evaluation functions to go with this deep search, and it's better to learn that from data. The computer can get a evaluation function that's much better than anything a human's got to figure it out. And for things like image recognition, people used to be doing a lot of work on things like wavelets or SIF features, things that are mathematically clean, like wavelets are mathematically clean and make a lot of sense, but they're not as good as what you can learn from just looking at data. And so that's the bitter lesson, that a lot of the effort that people have done is kind of wasted. And once you go up in scale, you shouldn't do that. You should just learn from data. Now, here is one leaderboard of current AI models. So this is the LM arena. So this is people asking random questions of the models and voting on which is better. And you can see there's a lot of different models here from a lot of different companies. So GPT 4.5 is the latest and greatest model from OpenAI, came out a month ago or so. Grok 3 is, I think GPT 4.5 and Grok 3 are the two biggest models in compute. Probably GPT 4.5 is the biggest model in compute. Gemini is Google's model, Claude is Anthropic's model, and DeepSeek is the Chinese DeepSeek model. And then there's Alibaba's Qwen down near the bottom. One thing that surprises me here is that it's really nobody is running away with it. That the models that are a few months old are losing to the models that are more recent. And people are continuing to scale up the compute, continuing to scale up to improve their architecture and optimization. And you can, I think, expect in the future that people are not coming up with real breakthrough ideas that give a large moat. That yes, the latest and greatest model is better than the previous model, but you fully should expect a new model to beat it in the next year. And it's not that much better. And so now that was for general chat bot. This is for coding. So if I ask my model to write a program, then there's actually a bit more variation here. I think Anthropic's Claude is noticeably better than all the competition. Maybe just break up the monotony a little bit. Let me switch to a demo here. So we can go to, you say something like, write a Sokoban style game in JavaScript. And let's do the extended mode, which means it's going to take a little bit longer. And when you do this, it starts thinking. Now, because it's going to take a little bit longer, it'll probably take a couple minutes. I already wrote one. I did it just a couple hours ago, and it came up with this. So here it is, and you can move and you can push the blocks. The Sokoban is the block pushing game. And when you do it, You win the level and you move to the next level, right? This took maybe a minute, maybe 2 minutes. If I were to try and write this program, right, you can reset the level, you can undo moves, you can go to previous level, next level. There's a lot of stuff here that, I could write this game, but not in an hour, right? Maybe in a day I could do it. Perfect, works perfectly. New move, right? And so the model is pretty good at entry-level stuff. Let's see whether so here it's done 50 seconds of thinking, and now it's writing the code. And the code, Claude's code is pretty reasonably well written. Here we got your HTML, your CSS, got the boards in a understandable ASCII way, and there it's done. So this is another attempt at the puzzle. This seems like a more interesting puzzle. Right. Yay. Yeah. So that took 2 minutes. You guys are making real progress. Is someone trying to talk? I'm hearing some feedback. Okay. So now let's go a little bit into the economics of that and where we are. So one H100 year. So the training these models, almost everyone, basically everyone except Google, is training on NVIDIA GPUs. So there, AMD has GPUs that are decent at inference, but nobody else has really cracked getting good enough GPUs for training other than Google and NVIDIA. And so these, so XAI and OpenAI and Anthropic are all trying to train on there's new clusters that have 100,000 H100s. Each H100 costs about $25,000 a year. There's a reason that NVIDIA stock price has ballooned enormously. So I was at OpenAI 10 years ago, and I remember people telling me to buy NVIDIA stock, and I did not do it. Poor choices. So if you look at that, so if you look at roughly how fast H100s are and how efficiently you can utilize them when training, or you can't use them 100% of the time when training, but more like 40 to 50% of the time. You can look at these different, let's just simplify, look at the OpenAI's GPT models, and say, how expensive was it to train? So from GPT-1 through to GPT 4.5, the number of parameters has grown significantly each time. GPT 4.5, I think, I don't really know what it is. I think for GPT 4, it's not public, but I think there's significant leakage about what it is at this point. GPT 4.5 is new enough that we don't have great leaks about what it is. But roughly speaking, each, from 4 to 4.5 was about a factor in 10 in cost, and getting to the point where training it costs hundreds of millions of dollars. And so if you want, and 4.5 is better than 4. It's slower than 4 and more expensive to infer as well. It's not that much better, and the cost will continue, right? Yeah. So will there be a GPT-5 that costs a few $1 billion to train? Quite possibly. But there's not that much headroom there to get bigger models. Now, before I go into the next bit I want to say, let's just go back to a bit more background. So a deep neural network is a long sequence of just matrix multiplication and nonlinearity. So you take your input vector, you multiply by some matrix A1, and then apply a nonlinearity, which is typically the rectified linear unit, ReLU, which just changes negative things to 0. And so you repeatedly multiply by a matrix, set negative things to 0. Multiply by a matrix, set negative things to 0. Multiply by a matrix, set negative things to 0. And repeat. And this is a shockingly powerful family of function approximators. And for an LLM, the function you're trying to predict is, again, given the text so far, what is the distribution of what the next word should be? And so you can train these parameters, right? The neural network is basically defined by what these matrices are. And so you just have these matrices, you scan through a giant corpus of documents, maybe 10 trillion tokens. I don't know, think of a token as a word. And for each word and the prior text, you want to maximize the probability of the word given the prior text. And so this, you can think of it as an improv engine. So this pre-trained model, this base model, it says, given the text so far, what is coming next? And if it's already made a mistake, then it says, oh, this is a text where the writer is making mistakes. Therefore, let me continue to introduce more mistakes, because I think that I'm trying to predict what the document would do. And if it's had mistakes so far, it'll probably continue to have mistakes. Right? It's not trying to be correct. It's not trying to be helpful. It's trying to mimic the corpus it was trained on, which was largely the internet. The internet is full of wrong information. And so it's getting into the voice of whatever this document is and trying to predict what, right? It's not trying to predict the correct answer. It's trying to predict somebody who was writing this document, what would they output as the correct answer? And so that's the state in pre-training, and then post-training tries to fix it. So there's two stages typically for post-training. So one is supervised fine-tuning, where instead of training on the whole web, you train on a supervised subset of data that's actually correct and helpful. It's like, this is actually how you want it to behave. But it's still a next token prediction. It's still estimating the probability distribution. And then there's a number of different methods like RLHF or DPO or PPO or GPO, where you try to not be predicting a distribution, but instead try to optimize an objective other than next token prediction. So you're trying to give correct answers or good answers or things like that. So you have some value function other than the probability of the data you're seeing. And this works. It sort of lobotomizes the model a little bit. If you compare the base models to the post-trained models, the post-trained models are better behaved, but it's sort of like they've been beaten with a stick, so that they're not as creative, not as intelligent as the base model was, if you access the base model properly. And there's an interesting meme about this, which is that you have your pre-trained model is this Shoggoth-like creature, and then supervised fine-tuning makes it look nicer, and then the RLHF is the cherry on top. They're actually friendly bit. But you're sort of accessing this thing we don't really understand, which is this base model. We don't really understand how to harness it as well as one would like. And so going back to the era of pre-training, so the table I showed so far that's the cost of pre-training, that Shoggoth-like entity, which is the dominant cost in training. But as you get to the hundreds of millions and maybe billions next time cost, it starts being important to look for other sources of advantage. And so, right, Moore's law has been important for any of this to work, but this scaling has not been Moore's law, right? This is, now that it works, let's scale up to what is feasible to do. And it's not feasible to scale it up that much more. And then then Moore's law continues, and we'll like scale up a little bit over time, but at a much slower rate. That you're, roughly speaking, spending 10 times more in each iteration and getting a noticeable but not huge improvement in each step. And so I think in the future, there will be movement towards more emphasis on other forms of improvement. So the architecture, the optimization, the data improvements to get similar base model from this for the same amount of compute for much less compute, or better post training to like harness it better, which I think has significant benefits. And then inference time compute is what we've been seeing with these reasoning models, where they make, which is basically a different kind of post training that says, let's make it at inference time when I'm asking the question, it'll spend 10 times longer, but get a 20% better question, the better answer. Now, that said, I'm not so sure that the area of pre-training is ending, because the most effective way we know to make a small model is to make a big model and distill it down to a small model. And so it seems quite possible that getting a few billion-dollar model and then distilling it down to something smaller that you can actually more cheaply run is going to be the best way to get models that can solve significant white collar work. And so one way to think about that is, would you rather pay $1 an hour for a 100 IQ assistant or $5 an hour for a 110 IQ assistant? Right? You're paying a lot more for the model, and it's not that much smarter. But if you're trying to do a task that is right, like the absolute cost of even GPT 4.5 is not that big to have it running all the time. Is not big compared to the cost of humans. And so if it gets to be 10% better, 20% better at the job you're trying to give it, that may well be a cost you want to pay. Right. So for things like coding, if it makes your software engineer be 10% more productive, then that's worth an enormous amount. That's easily worth another factor 10 scaling in cost. I think the bigger problem is not the cost of doing it, but the cost that it is hard to train if it gets that expensive at infinite time. All right, so just concluding that this thought on the state of AI, or the current AIs are superhuman at knowledge and mediocre at reasoning, I would say. Now, one thing that takes a bit of an adjustment is that they fail differently from humans, particularly because they will be extremely confident and fluent in describing total nonsense sometimes. That they want to output something, and they know they're like really good at writing like an expert, even when they're doing nonsense. And so if you're not checking them carefully, it's easy to be misled. This is different from humans, right? Because if you take a junior grad student, you give them a problem, they don't solve it. Even when they think they've solved it, they make a mistake. If you read it, it's sort of clear that they're not sure what's going on, that they're not very familiar with this thing, and the style of it gives red flags that something has gone wrong. While for the AI, the style does not. The style sounds like it's somebody that's totally on top of things, knows everything that's going on, and then you take a lot more effort to identify where the bugs are in the AI's work. And there's a thing that the bigger, better models are better at, but not that much better at. And so it remains a significant issue. But still, I think at a large fraction of tasks, it is better than most people. Even for experts, it's better at most of the things that they are doing. There is no software engineer who can write that Sokoban game as fast as the AI did. And so I think, basically I am not that interested in going back to proving theorems in CS theory, because I think within 10 years it'll be clearly doable. Most of what I would do now will be automated away. And I think that is the case for a lot of work. Now, I think these models are not great at generalizing. Right? They take a ton of data to do a good job. They need to have seen a lot more examples than humans need to have seen. And so it's not clear to me that they will make their way all the way up the value chain. But I think that for the jobs that there's a well-established training pipeline to teach people how to do, that well-established training pipeline generates a lot of data that the AIs can use to become just as good as the humans, and then better. All right, so that is my thoughts on the state of AI. Not sure if I have how much time I have and how much I want to be going into our presenting our model. Yes. Daniel?
No, yeah, I just noticed that you have more. I'd prefer to hear more of what you have to say. Looks like an interesting slide after your conclusion slide.
Yeah, so yeah, basically, yeah, I wasn't sure quite what the audience here is. So this is going to be a little bit more technical. I'm probably going to race through it. But so this is a model that we built at Microsoft Research. There's like 27 of us. And it's a 14 billion parameter model. So this is significantly smaller than the really frontier models. And relative to in the Phi series, which is driven by synthetic data. So being at Microsoft is the one that is hosting GPT-4o, so we have a lot of easy access to GPT-4o inference. And so the question is, how do we use this teacher model where we can ask for a bunch of GPT-4o generations to train a new model? And we did this, and we get a model that is, so 14 billion is pretty small, but it is quite good at math contests. So I gave it the November 2024 AMC 10 and 12, and it beats what were state of the art at the time, although some of these are no longer state of the art. This was back in December. All right, and trained on 10 trillion tokens. So there's a table, which if you know about benchmarks, there's a bunch of different benchmarks. And so currently we have these reasoning models that spend much more time at inference time, but this is more expensive to compute. So just in general, how this works. So we start by generating a bunch of synthetic training data, which I'll go into in detail. And then we pre-train the model at this 4K context length. That means 4,000 words predictions for 10 trillion tokens. And then we do mid-train to extend the context length because it's slower to train at longer contexts. And then we do post-train for alignment. And so each of these stages is getting fewer tokens and a lot faster. And the philosophy behind 5.4 is that we like synthetic data because imagine you want to be accurate on math competitions and you collect 100,000 questions. Would you rather have human organic solutions or synthetic GPT-4o solutions? And in some cases, the organic solutions are not very good. So here's a math contest that I was involved in. If you look at their website, and look at the solution starts with the answer. And in a next token prediction model, it's very hard to predict 2006 immediately. Right? The human wouldn't be able to write that immediately. Right? That's not how the human solved it. The human first figured out the solution and then came up with the answer and then put the answer back at the beginning of the solution. And so expecting the model to immediately say 2006 here is too hard for the model. It's not something that the model is able to do. And so by doing a synthetic generation, you make sure that it's not going to have these mistakes, these badly formatted data, that each token is at a reasonable difficulty level for a large language model. And the other advantage is that you can target the data more precisely. So you're placing, like if I'm going to ask a chatbot for this data, then it's easier for the chatbot to retrieve it if it's been trained on chats with the information rather than general stuff. And so it trains faster and needs less data. And the downside is that it's somewhat mode collapsed, and it's inheriting the teacher model's idiosyncrasies. So for example, and so we had 75 different pipelines to generate 580 billion tokens. So as one example, suppose we take a web page. We can then ask GPT-4, okay, is this find an interesting excerpt of this web page, and then generate a conversation about this excerpt. And at various stages, you can judge it to see whether it's good, and then you can just see whether it looks good. So as an example, you take some website that's talking about Herman Miller and its Lean Enterprise Institute success story. And now you don't want the chatbot to be able to generate this web page because it's not going to be generating this web page. You want it to be able to generate conversations about this web page. And so you can construct a conversation about it. We're like, okay, well, let's have a user ask this question and the assistant responds, blah, blah, blah. And that's this web rewrite idea. For math synthetic generations, you suppose we have 1 million question answer pairs. The problem with this, if you have 1 million question answer pairs, right, that's a lot of math questions. It's hard to get 1 million question answer pairs. But it's also not that many tokens, because the solution, like each pair is going to be order of 1,000 tokens. So this would be like order of 1 billion tokens of math question answering. We want to train on 10 trillion tokens. So you don't have nearly enough data to actually get close to the scale you want. And so what we got to do is synthetically create variants of these problems. So you ask for how to, you give it a problem, you ask GPT to generate a variant of the problem, then you solve that problem, then you throw that into your training data. So overall, we have 580 billion synthetic tokens, 2.7 trillion organic tokens. We find that the synthetic data is more useful for increasing scores. And so at training, we do like 12 epochs on the synthetic tokens and 1.5 on the organic tokens. Some of the organic tokens are better data, and so we do more training on them. And then we do post-training, which we have this idea that we call pivotal token DPO, which I guess I'll go into now. So here's a math problem. And so, suppose the roots of some polynomial or A, B, and C, find T, wherever under this thing, right? So if you ask GPT-4 to solve this problem, you can ask, at the beginning, it has a 20% success rate. That means if I generate 100 times, it'll get roughly 20 of them will be correct. Now, if you take some correct solution, such as this correct solution, and then you were to start halfway through the solution, the chance of success will be something other than 20%, right? It starts out being 20%, but if I were to regenerate from the middle, it might be more, it might be less. If I regenerate from towards the end, it'll be 100% because it's a correct solution. And what we find is that there's a few locations where the probability jumps a lot, which is where the model, either it makes a mistake or it isn't making a mistake, but it's making a choice that's going to cause it to make a mistake in the future. So in this case, this corresponds to the negative of the product of the roots, blah, 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 blah. And if it doesn't say negative there, if it says product of the roots, which is what it prefers to do, then it's likely to forget to take the negative sign in the end. And so by having it say negative here, it's not going to make that negation at the end, and it's going to give the correct answer. And so you identify these locations where the model has been going astray, and by correcting those, you increase your performance by a few percent. We have some other post-training for hallucination mitigation. So teaching the model to say, I don't know, is a bit tricky. Because in pre-training, you sort of want to teach it stuff. You don't want to teach it to say, I don't know. You want to teach it the information. And so we mostly do it in post-training. And basically, you can take a challenging QA because we don't know in pre-training how good it'll be, like how much information we can cram into this 14 billion parameter model. But then in post-training, you can evaluate what level of problems it knows, what level of problems it doesn't know, and then you teach it to say, give the correct answer when it knows, and to say, I don't know when it doesn't. And so that's 5.4. So it's at this Pareto frontier where it is fairly small. So you can run it on your consumer gaming GPU. It's open weight. You can download it under an MIT license. And it's pretty good at math, science, and coding, and doesn't use a ton of inference time compute tokens. So it's pretty fast in how it responds. You can read more about it on the archive or check it out on Hugging. Again, it's nice performance on math content. All right, that's it. Yes, Daniel.
Kurt, can you hear me now?
Yeah.
Excellent. I have a question for you, maybe just thinking a little bit toward the future. And that is it seems to me that we're right now sort of in the steam engine era of the AI models. We really don't have a good understanding of precisely how they work, the theory of why they work. It seems to me that somebody will figure that out, and then there'll be another step change in the capabilities of the AI models because we have figured out how to make them work much better. It's a software problem in my mind. What do you think of that hypothesis?
Yeah, so I think the steam engine phase of deep learning is an analogy that people were talking about when I was at OpenAI 10 years ago. And so that certainly I agree with. I'm not sure I expect a step change in performance. I mean, I think people are doing a ton of tinkering, and as they do tinkering, they get improvements in the architecture, improvements in the optimization, improvements in how to construct the data. Right? Like people are coming up with improvements here.
Maybe I can amplify my question a little bit. The step change I mean is similar to the step change that occurred when we went from steam locomotives to diesel engines. In other words, it all of a sudden, people may not be aware, but steam engines are really a lot of maintenance, huge amounts of fuel because they use relatively inefficient mechanisms to generate motion. But by doing a completely different type of model, an internal combustion model, a whole lot of efficiencies were obtained and performance was greatly increased at much less cost. That was a paradigm change. In other words, it was literally throwing out the old stuff. Imagine how that's going to affect the bottom line when you have to throw out all your H100s because we're now doing something different. That's the type of thing that I'm hoping for, and it's hard to predict. The diesel guy, he was a nobody. The guy by his last name was Diesel. And he mysteriously ended up dead somehow crossing the Atlantic. But that's sort of the danger as well, because if we make these models step change or quantumly better than they are now, and we ask the model, please start improving yourself, and if it can, then we get sort of a runaway situation. What do you think of that?
Yeah, so I don't know the history of steam engine to diesel transition very well. I think so. All the models that were on the leaderboard there were in this autoregressive large language model paradigm. Though it's not the only game in town. There are other models. So there's diffusion large language models that are currently a generation or two behind in terms of performance and language. So these are diffusion models are mainly used in, right, they are leading leading the pack in image generation, but they're not as good at language models. But there's still there's value there. There's some differences in what they're good at, and so they're an interesting direction. Yeah, I don't think you would throw out the H100s. Like, I think whatever happens in the future, it will still rely on the compute that we have, and we're still rely on tons of compute. It'll still rely on it'll still rely on the having tons of data. It'll still rely on optimization. So it may be a different architecture, but I think most of the work coming in here won't be that affected. Yeah, I mean, I think you do expect. I have seen people claim, and I have not checked carefully, that the algorithmic improvements have been comparable to Moore's law in efficiency improvement. I don't know. Yeah, that seems plausible to me. Yeah.
Thank you.
Oh, yeah, time is 7:30. Is there any other question from the audience? Please unmute yourself and raise your hand or just talk.
I saw a question on the chat. I don't know if it has been answered
Oh
yet.
yeah. Yeah. So if the entry level jobs are eaten by AIs, where do we get senior employees? It's a good question. I kind of think it's likely that there's a decent chance that the senior employee jobs get eaten before you need more senior employees. Not clear, but I think there's a decent chance of that. The other aspect is I think, like, how do you get good as a senior employee, as a manager of people? By experience doing it. And if you can, if everybody can manage AIs, then you actually can get this experience much more easily. So I think it should be doable. I don't think there is that much skill involved. And so if the AIs aren't able to do it, and there's some ineffable human touch here, I think humans will manage it.
Eric, I ask you a question about your career choice. You don't want to do the theorems or the proofs anymore because the machine, like a chess machine, will do the proofs much faster. But might I suggest that I think there's going to be a demand for people who can think of outside the box theorems. In other words, using the automatic theorem prover as a power steering, just like we don't walk everywhere we go today, we take a car. That's a way we're using the machine to make us much more productive in the case of a car and travel. But in your case, using the AI theorem provers or generators, I'm unfamiliar with your field.
Yeah. So basically, I think if the AIs plateau and they get stuck where they are a year or two from now, then that makes a lot of sense. It's still the case that I don't think it makes sense. Like, it's like, if you were chopping down a forest and you have a regular axe, you've ordered a chainsaw that's arriving in a few weeks, then you shouldn't chop down trees right now. You should wait a few weeks and then use the chainsaw. Like,
Yeah, yes, but that's still super important. You know which trees to chop down. And that's where somebody like you comes in with the theorems because you know the theorems from a manual perspective, and now you have a chainsaw or a fleet of
yeah.
chainsaws.
So
And
the thing is, I'm not sure that my skill at that is that great. That it kind of seems to me like if you have 1,000 AIs that are each superhuman at proving lemmas and just have them explore the space,
but that's a
that
brute, but there's an indication where your human intuition might be valuable because a brute force attack of exploring the space is something I would do because I have no idea what I'm doing in your field. But you having a much more experience in the lemmas and so forth.
yeah, so it's like that's not how chess worked out. That there was a time in which chess plus AI was better than either chess or AI.
Yes.
It was a very brief period before the AI were just better. And now like there's no point, and now you assume that your phone is better. Like now the phone is far, far better than Magnus Carlsen, and he would have no chance. And yes, there will probably be a few year period in which I have significant value add, but I'm not convinced it'll be many years.
What about the hallucination problem?
Yeah, that needs to be addressed. Right. So that's something that I'm certainly interested in trying to solve. Um, yeah, that needs to be addressed. I think it
Okay.
should be doable, but it's
Great
possible
presentation.
that they plateau.
Excellent presentation, by the way. Very intriguing.
Well, Eric, if quantum computing will get better, will be more useful, will it help the AI development?
If what computing?
Quantum computing,
Oh,
you can look at more data, process more data.
I don't really expect it to at any near-term scale. Yeah, like the near term, the near-ish term benefits of quantum computing are mostly in like simulating quantum systems. If you want to simulate quantum physics, then quantum computing is very promising. Um,
Okay.
but that's the main thing.
So to all our audience, any other questions?
I have a question that may be totally unrelated, but noticed a week or two ago there was a big flap in the stock market for AI companies and in the popular press because there was a model from China that somehow seemed to be trainable for pennies on the dollar. Would you care to comment on what happened there?
Yeah, so I would say it's not so that was DeepSeek, and you can find it in the leaderboards they had. I would say it's not pennies on the dollar. I think people had I would say it's more like 20% the cost, 20 to 30% the cost. That people had a unrealistic view of how expensive the comparable models were to do pre-training. That's just one piece of a much larger system where you need to get all the data, you need to write the code, you need to do the infrastructure. Like there's a lot more. Like that was the marginal cost of one pre-training model. That was like $5
I
million.
see.
Now, I do think it is reasonable for the stock that I do think that DeepSeek was a big deal because it is a very good model and it poses, it is right. So it's not as good as the very best American models, but it's pretty close. And at least for the moment, they are open sourcing the weights. So it's not the source code, but the weight, so you can run it locally, which emphasizes that these models are kind of commodities. And so so basically OpenAI's valuation assumes that it can extract monopoly rents from having the best model. And if it can't extract monopoly rents, then, well, it probably can't make that much money, and then you can't invest as much in it. All right. So I think there is good reason to be for a revelation when not all of the top models are American. Right. So now if you look at the leaderboard, there were probably 4 American companies and 2 Chinese companies on that leaderboard. And yeah, and where we will be in 2 years, I don't know. I think there are, right? So it's not clear that DeepSeek will get the export controls for the moment are, I think, going to be more effective. But they're also driving Chinese chip manufacturers to figure out inference or figure out training. So I don't know. But basically, I do not think that there's a question of how far behind China is and the best Chinese models will be. And I would say currently, DeepSeek, previously you thought they were a year to 18 months behind. Now it's more like 6 months behind, if that. And now, how important is it to be 6 months behind, 6 months ahead or a year ahead? Like, it's not. There are people that imagine that the singularity is near, and you get to the singularity. What matters being first the singularity, because then you win. But what does win mean? Like bombing China, like with your power thing? Like I don't think that anyone is prepared to go to war over this. And so then being 6 months ahead doesn't actually matter. So yeah.
In
Thank you.
your product comparison chart that you presented earlier, it looks like you're missing the Llama, the Meta's product. Is that a reason why you didn't compare them? Because
Sorry, in which one?
the Llama,
Yes, but where was I missing it?
well, when you compare a bunch of products in the early 2 pages,
Oh yeah,
they're not in the
because
picture.
it's not on the leaderboard. It's not good enough.
Not gonna. Okay.
Yeah. Right. So I think that is maybe an update from the DeepSeek that like it sort of shows that Meta was really dropping the ball with Llama.
I see. I thought they're open source. It looks like they have more support if they're open source.
Right, but right. So basically, the open weight models, they were the best open weight model, but now both Alibaba Qwen and DeepSeek are just better and open weight, and so Meta has dropped the ball.
I see. Okay. So right now it's 7:44. Any other question from the audience? And if not, then I will thank Eric giving us such a great presentation. I didn't understand most of the stuff you present, but especially some of the formulas. So I hope the audience will learn something at least. Okay. Thank you.
Bye.
So see you For those who are interested, we have a 6G talk in 2 days. In April, we have a marketing talk about a hobby of a UT professor, a marketing professor. So you'll see in the letter, newspaper, newsletter. Okay, bye-bye.
Thank you. Bye.
Okay. So Louis, you're gonna send me some of the
Yes.
headcount. Okay. All right. Okay. Thank you.